Alright, in this video, we study the convergence or divergence of a sequence. And in particular, pay attention to how we define rigorously what it means for a sequence to converge or diverge. Alright, let's start. So we consider a sequence of numbers such as A1, A2, and so on. So this index 1, 2, 3, and so on goes to infinity eventually. And A1, A2, these are real numbers. Okay. So in general, we write sequence like this. So AN enclosed in curly brackets, and this N varies from 1 to, well, sometimes not from 1, but usually from 1 to 3, and it goes to infinity. And this order matters, the sequence A1, A2, A3, and so on. This is different from A2, A1, A3, and so on. Okay, it's not a set, it's a sequence. Okay, to stress it's a sequence, we may write like this, and from 1 to infinity. Okay, and if this sequence approaches some constant value as n goes larger and larger, then we say this sequence converges, and the limit of an as n goes to infinity is some constant alpha. So this is the converged value. We say it's a converging sequence. Or if it's not the case, then we say the sequence diverges. Okay, converges to alpha, or it diverges. So it can diverge to infinity or negative infinity, or it doesn't, diverge to any of these, but it can oscillate or it can take random values or whatever. In any case, it doesn't converge. We say it diverges. And instead of writing like this, we sometimes write like an goes to alpha as n goes to infinity. See a few concrete examples. Suppose we have a sequence of an where an for each n is defined as negative 1 to the power of n over n. Then so the first several terms of this sequence are this. When n is equal to 1, we have negative 1. When n is equal to 2, we have 1 over 2. When n is equal to 3, we have negative 1 over 3, and 1 over 4, and negative 1 over 5, and so on. And as you can see, each term gets smaller and smaller as n increases. So eventually, we can show that this converges to 0. So the limit of this sequence is 0. Or we can write this goes to 0 as n goes to infinity. And here's another example of divergence. Suppose we have a sequence of an where an is given as 3n minus 1. Okay, so the first several terms of this sequence is this. So when n is equal to 1, we have 3 times 1 minus 1, so that's 2. And the next one is 5 and 8 and 11 and 14 and so on, and it becomes bigger and bigger as n gets bigger and bigger. So it doesn't converge in this case. And in fact, it diverges. So, and it goes that diverges to positive infinity. So we write like this: 3n minus 1. It goes to positive infinity. Okay, so don't confuse this as convergence. When we write infinity, infinity is not a number. It's just a limit where we mean some arbitrarily number, okay, arbitrarily large number, positive large number. So we say this sequence diverges to positive infinity. And of course, there are some sequences that diverges to negative infinity. For example, if we have a sequence of ANs where AN is defined by, say, negative n squared. So the first several terms of this sequence is -1, -4, -9, and so on. And it gets arbitrarily large negative number, okay, as n goes to infinity. So the limit of this sequence is negative infinity, and it diverges to negative infinity, okay? It doesn't converge to negative infinity, it diverges. There are some sequences, it doesn't diverge to positive or negative infinity, or it doesn't converge. For example, let's consider a sequence where an is -1 to the power of n. Okay, so this one oscillates between negative and positive 1. Okay, so the first few terms are like this: -1, +1, -1, +1. So it just keeps alternating between positive and -1. So this limit doesn't exist. So it doesn't diverge to positive or negative infinity, or it doesn't converge either. Does not exist. So what do we exactly mean when we say a sequence converges to a certain value? Again, let's consider this sequence, -1 to the power of n over n. So we said this sequence converges to 0. So let's make a table of the terms when n goes from 1 to some large value. Okay. When n is equal to 1, then an is what? It's -1. When n is equal to 2, that is 1 over 2. And if we keep increasing, when n is equal to 10, then an is, it's 1 over 10, so let's say 0.1. And when it's 100, n is 100, then it's 0.01. When n is 1000, it's 0.001. And when n is 10,000, it's 0.0001. So, we said this converges to 0, and as n increases, the value of an decreases, so it just gets smaller and smaller. And actually, the difference between an and 0 becomes smaller and smaller. So this is just this. So it becomes 1 when n is equal to 1, and 1 over 2 when n is equal to 2, and so on. So it becomes 0.0001 when n is equal to 10,000. Okay, so this difference can become arbitrarily small. So that's what we mean by convergence. Okay, so let's say we pick a very small positive real number called epsilon. Okay, so can we make the difference between an and 0 less than epsilon? Is it possible by taking some appropriate value of n? Yes, it's possible if it converges. So if an converges to 0, then for whatever the value of this epsilon is, if this n is large enough, then this inequality eventually holds. Okay, so if n is large enough, then this is always true. Okay, so we adopt this intuition as the definition of convergence of a sequence. Okay, so here's the definition. So we say the sequence AN converges to some constant alpha if the following condition holds. So this is the definition. If and only if the following holds. That is, for any epsilon that is positive, there exists some natural number, let's say natural number capital N, it's a natural number, such that for any natural number lowercase n, if n is greater than lowercase n is greater than or equal to uppercase n, then the difference between an and alpha is less than epsilon. Okay. So this is the definition. So what this means is that however small this epsilon is, we can always make the difference between the term and the convergent value less than that epsilon. Okay, if we take large enough n. So large enough means, so there is some large number n. So if the index is greater than that certain large number, then this is always true. Okay, the difference is always less than epsilon. So this epsilon can be very small as long as it's positive. Okay. By the way, so when n converges to alpha, we write, as you know already, like this. Or an goes to alpha, converges to alpha when n goes to infinity. Let's see an example. Consider a sequence defined by an equal to n over n plus 1. And we can show that this sequence has a limit, or it converges, and the limit is 1. Okay, let's see this in the context of this definition. Okay, let's say epsilon, epsilon can be any positive real number. So let's say epsilon is 0.01. Okay, so if we know this is 1 is the convergent value, so an minus alpha, so that will be n over n plus 1 minus 1. So can we make this less than epsilon by taking large enough n? So how do we do that? First of all, this absolute value, we can get rid of this absolute value by doing this. Because n over n plus 1 is always less than 1, so 1 minus this is always positive. So the absolute value of this should be this. Okay. So this inequality means this less than 0.01 in this case, because we set epsilon is less than 0.01. Okay. Then from this we have n over n plus 1 is greater than, what is it? 0.099. And from this 0.99 n plus 1. So that is, let's see, so that is 0.99 n plus 0.99. So let's see, 0.01 n greater than 0.99. So n is greater than 99. So if this holds, then this holds or this holds. Okay. So in this case, the critical value of this n should be 100. So the definition of convergence was this. For any epsilon that is positive, there exists some natural number, capital N, such that for all natural number, if lowercase n is greater than or equal to uppercase n, then the difference between the term and the convergent value is less than epsilon. So in the present case, we set epsilon as 0.01, and if we set n as 100, then for any natural number n, as long as this lowercase n is greater than 100, greater than or equal to 100, then we can set this difference between the term and the convergent value less than epsilon. Okay, so in this case, it's n over n plus 1 and minus alpha is less than 0.01. So it's achievable. Okay, next, let's prove that the sequence 1 over n converges to 0. Okay, maybe you think this is obvious, but it's good to be able to prove something obvious if you want to. Okay, so let's do that. So how can we prove this? Let's go back to the definition of convergence. So if this is true, then what this means is the following. For any epsilon that is positive, there exists some natural number, capital N, such that for all natural numbers, if this lowercase n is greater than or equal to capital N, then the difference between 1 over n minus 0 is less than epsilon. Okay, so what does this mean? Okay, consider this part. So 1 over n minus 0 is 1 over n, and of course this inside this is positive, so it's just 1 over n. So if this holds, then we should have this. Okay, but on the other hand, we also should have this. Okay, if this is true, then this is true. So if lowercase n is greater than uppercase n, so now we have 1 over n here. So let's change this to 1 over n form. So that would be 1 over n should be less than or equal to 1 over capital N. Okay, let's combine this and this. So that means 1 over n is less than or equal to 1 over capital N, and this should be less than epsilon. Okay, so the problem is finding this n. Okay, so this epsilon can be anything as long as it's positive. How can we find this n? So from this inequality, we have 1 is less than epsilon times n. So if we can prove that we can always find some n such that this inequality holds, then we are done. But remember, we can use something we have already learned. Okay, so from here, let's start the proof. Okay, so here's some preliminary study about the strategy of proving. So this one, we can use Archimedes' principle. Okay, so let's start the proof. Let epsilon be any positive real number. Okay, by Archimedes' principle, so there exists some natural number n such that epsilon times n is greater than 1. Okay, remember Archimedes' principle? It was like this. If a and b are any real number, if a is positive, then there exists some natural number such that a n is greater than b. Okay, so that's exactly what we have here. In this case, this a corresponds to epsilon, and this b corresponds to this 1. Okay, so by Archimedes' principle, this is always possible. So That means, so now we can reverse this argument here. So this is all, we can always find such a natural number. So that means for any epsilon that is positive, there exists some natural number n. So this natural number n can be found according to the Archimedes principle. So since this holds, if lowercase n is greater than or equal to this uppercase n, then we always have, so since we have epsilon times n is greater than 1, so that means if this is true, then epsilon lowercase n is always greater than 1. So that means 1 over n is always less than epsilon. Okay, so let's skip this. So from here we can conclude this is true. So this is true. So of course this is true. Okay, so it's done. Therefore, 1 over n converges to 0 as n goes to infinity. By the way, this value of n depends on the value of epsilon, okay? That means first epsilon is given, and for that epsilon we choose appropriate n, okay? It's not the other way around, okay? If it's the other way around, that means this. So this, first for all epsilon, then there exists n. So if we swap this order, what does that mean? There exists some natural number such that for all epsilon that is positive, then the rest is the same. Okay, for that means this. So and the conclusion is 1 over n is less than epsilon, right? So that means we also have 1 over capital N is less than epsilon. Okay. So if n doesn't depend on epsilon, so that means this. There is some natural number n such that for all epsilon, this is true. But this is nonsense. Okay. What this means is that, as we have seen in the previous video, if this inequality holds for any epsilon, any positive epsilon, that implies 1 over n is equal to 0. Okay, but this cannot happen because n is a natural number. It's a concrete natural number. It's not a limit. It's a natural number. So it's always 1 over n is always positive. So it cannot be equal to 0, not exactly equal to 0. Although it can be very close to 0, but it's never 0. So this is nonsense. So this order for all and there exists, that is important. So this is wrong and this is correct. Okay, next let's see an example where the sequence doesn't converge. Okay, wait a minute. Okay, so an is equal to -1 to the power of n. So obviously this doesn't converge. It just oscillates between positive and -1. But let's show that this indeed does not converge. Okay, so to prove that, we use proof by contradiction. Okay, so suppose this an converges. So converges to some value alpha. Okay, so alpha is some real number, constant. So then there should be some natural number such that if natural number is greater than or equal to capital N, then the difference between an and alpha is less than, let's say, 1. Okay, so epsilon can be any value. So let's pick just one for simplicity. Okay. Now, if n is even, then an is -1 to the power of n is +1 because n is even, so it's 1. So we have 1 minus alpha. The difference between 1 and alpha is less than 1. Okay. So this means this inside this is between -1 and 1. Right? So in particular, let's focus on this part. From here, we can conclude that alpha is greater than 0. So alpha is positive. Okay. On the other hand, if n is odd, then an is -1. Okay, so that means -1 minus alpha is less than 1. Of course, -1 minus 1 is 1 plus alpha, right? So we should have this. And from here, we have this 1 plus alpha is between -1 and +1. So in this case, let's look at this part. Then from here, we conclude that alpha is negative. So although alpha should be a constant, on one hand, it's positive. On the other hand, it's negative. So no real number can be both positive and negative at the same time. So it's a contradiction. So this is a contradiction. So the initial assumption was false. So this was a false assumption. By contradiction, this sequence doesn't converge. Finally, let's define the divergence to positive or negative infinity. Okay, so we say a sequence diverges to positive infinity if and only if the following condition is satisfied. So that is, for any real number, let's say m, there exists some natural number, capital N, such that for all natural number, if this lowercase n is greater than uppercase n, then an is greater than m. Okay. So this is what we mean by diverges to positive infinity. So this m can be any real number. So it can be very large positive real number. So however large this is, we can always pick some capital N such that if the index is greater than or equal to that n, the term of the sequence is greater than the value of m. Okay, so that means as n goes larger and larger, an becomes arbitrarily large. And the divergence to negative infinity is similar, but we just swap the inequality. Okay, so this means an diverges to negative infinity. That means for any real number m, there exists some natural number, uppercase n, such that for all natural number lowercase n, if lowercase n is greater than uppercase n, then an is less than m. Okay, so this m can be any real number. So it can be very large negative real number. But however large that is, we can always find some n large enough. So if the index is large enough, then an is always less than that m. So that means this an can be arbitrarily large negative number. So that's what we mean by diverges to negative infinity. So that's all for this video. But the way we define this limit using epsilon-N argument is actually quite hard to understand at first. But please get used to it, and please review the definitions again and again until you find it natural, because it's so fundamental, and we are going to use it everywhere in the future. Okay, so that's it. See you later.